Dart and bicycle wheel. A bicycle wheel of mass M and radius r is placed on a vertical axle and can rotate without friction. A dart of mass m, so please don't confuse those, is fired towards the wheel with an initial velocity v0. The dart strikes the wheel and sticks in the tire. The moment of inertia of the wheel is I equals mr squared. Consider the system as the dart and bicycle wheel. What is the magnitude of the initial linear momentum of the system? B. Is the linear momentum of the system conserved? Explain your answer. C. Is the angular momentum of the system conserved? Explain your answer. D. What is the magnitude of the angular momentum of the system with respect to the center of the wheel right after it is fired? E. What is the magnitude of the angular velocity of the system after the collision? And F. Find the ratio of the initial kinetic energy of the system to the kinetic energy of the system after the collision. What is the magnitude of the initial linear momentum of the system? Use the definition of linear momentum, and the only object in the system that is moving is the dart. So it's just going to be mv0. Is the linear momentum of the system conserved? No, linear momentum is not conserved when there is a net external force. The axle is exerting an external force on the system. Is the angular momentum of the system conserved? Yes, it is. Angular momentum is conserved in the system since there is no net external torque. The forces between the dart and the wheel are internal action-reaction forces and do not exert an external torque. There is the external force that the axle exerts on the wheel, but it is exerted at the axis of rotation, so it does not provide a torque. Find the angular momentum. Construct a triangle with the direction of the momentum mv0 over here, the distance r to the axis of rotation, and the angle theta between them. The magnitude of the angular momentum would be rp sine theta, and our r is the capital R. Here's the linear momentum that we found earlier, and the sine of the angle between mv0 and r. What is the magnitude of the angular velocity of the system after the collision? And when considering that about the axis right here. Calculate the moment of inertia of the system. Well, it's going to be the dart and the wheel. The wheel, we've already been given this, it's mr squared. The dart is also mr squared, but what's different here? This is a little m, this is a capital M. This is the wheel, this is the dart. And why is it mr squared? It's a distance r from the axis of rotation. Now use the definition of angular momentum. L is I omega. Solve for omega. Substitute in what we've calculated on the previous slide for the angular momentum. Here's our moment of inertia, and our answer is this. And one more caution, do not confuse lowercase m with uppercase m. Find the ratio of the initial kinetic energy of the dart to the kinetic energy of the system after the collision. The initial kinetic energy is all translational. We've just got the dart moving. The final kinetic energy is all rotational as the wheel rotates but does not move linearly. So we set up our ratio here. Kinetic energy of the dart, 1/2 mv squared. Kinetic energy of the dart wheel system, 1/2 I omega squared. We're not done yet though. Now it's just a matter of substituting in our values for v and I and omega. Okay, so here's our top, there's our v0, here's I, here's omega. Now it's just a little algebra. So please feel free to pause the video now and work this out for yourself. And eventually you should be getting this.